Yes, calculus 2. So, what we do here is something very simple. Calculus 2. The first thing, standard integrations and algebraic substitution. Standard integrations and algebraic substitutions. The second thing we'll talk about, so under standard integration and algebraic substitution, there are a lot of things we are going to see here. How to integrate a polynomial function. How do we integrate a polynomial function? How do we integrate an exponential function? How do we integrate a logarithmic function? How do we integrate a trigonometric function? How do we integrate a hyperbolic function? How do we integrate an inverse function? How do we integrate an inverse function? How do we integrate integrals involving partial fractions? We want to see how we will be coping with integrals involving partial fractions. Then after that, we shall talk about integration by parts. Integration by parts. After integration by parts, we shall talk about integration of a function in the form. Integration of a function in the form. Let's say, for instance, f of t to be equals to maybe 1 over a sine t plus b cos t plus c, where a, b, and c are constants. You see, what this means is this. When somebody gives you a problem like this, let's say, for instance, integrate 3dx over 2 cos x. So this is a function in this form, meaning you are integrating a function f of x dx, where f of x is 1 over 2 cos x, because these three are constant and we factor ourselves at the integral. Are you seeing that? So it means 1 over 2 cos x is f of x, where if this 2 is a constant, maybe b. So it means a is not there, a is 0, that is why sine x is not there. Are you seeing? C is 0, that is why the constant term is not there. So we'll see such problems. How do we integrate a function having that standard form, isn't it? Because somebody will come again and give you integrate dx over cos x plus sine x, or over cos x plus sine 2 sine x, isn't it? All those are functions in this form. It's only the variable we changes. They can be t, they can be x, they can be theta, they can be anything, isn't it? Very common. That case is very, very common. The next, of course, the reduction formula. I'm not going to dwell much into reduction formula. What I will just utilize the reduction formula. What I will just deal with is what you learned in trigonometry. Trigonometry 2. The trigonometric identities. We'll just be dealing with those identities to see how do we integrate certain functions maybe the trigonometric functions, like someone tells you to come and integrate sine raised to power 6x dx. Have you seen such a case? Have you seen such kind of cases?
Yes.
So such case is very easy to integrate when you use trigonometric identities, because you can actually use from complex numbers. You can use the De Moivre's theorem to get rid of the power to express sine raised to power 6x in multiples of x, isn't it? Have you seen that? So instead of going any other long process, you just use that De Moivre's theorem to remove the power to express it in form of this multiple angle, isn't it? Then you are able to do that, because you cannot integrate it when it is raised to a power. You must get rid of the power. And the only formula which can get rid of that is De Moivre's theorem, isn't it? So it means that the reduction formula will not be working much in our case, okay? Then the next thing, application of integration. Applications of integration. Applications of integration. So here, the first thing we are going to talk about is the mean value. So we shall talk about the mean value. What is the mean value? Then after that, we shall talk about the root mean square. The root mean square, or sometimes the standard deviation. The root mean square of the standard deviation. Then from there, we shall talk about area and the curve. How do we determine the area and the curve? After seeing how to determine the area and the curve, then we shall talk about the centroid. How do we determine the centroid of an area bounded by maybe 2 curves, 3, 4? You see, in such cases. Then after seeing how to determine the centroid, then we shall see how do we determine the volume of revolution. The volume, if maybe you rotate a certain curve about x-axis, you rotate a certain curve about a certain axis or a certain line, isn't it? How do you get that kind of volume of revolution? Then from volume of revolution, we shall go the integration by using the normal integration approach. Then the second part, we shall now deal with the Pappus theorem. How do we use the Pappus theorem to determine the volume of revolution of any curve? Okay? About x-axis, very important, because let's say for instance, if this is an xy plane, then you have this curve, you will go to this curve y is equal to x squared. So if you want to rotate this curve about y-axis between the points of values of x, 0 and 1. So if this is the area you want to rotate, meaning when you will be rotating it, it is like you will be getting a cylindrical figure, isn't it? About the y-axis, isn't it? So cylindrical figure is not the volume you are looking for. You are looking for the volume of this shaded part, meaning you are going to subtract this volume of something or in form of a semi-hemisphere shape, isn't it? You have to subtract this one because that is not part of it when you are rotating it about the y-axis. Are you seeing? But when you are rotating this same shaded region about the x-axis, it means the volume you are getting is direct, because the whole of this part about the x-axis means it will be moving like this, isn't it? This is now the volume you are looking for, meaning the whole volume, there's nothing you are subtracting, isn't it? But when it is about the y-axis, you must subtract this part, which is not there, isn't it? So that must be, you must always be very keen when you encounter such cases. Let us have the reason. These are two different things. Standard integrations and algebraic substitution are very different things, but I do combine them in that a lot of functions, maybe you wanted to integrate a logarithmic function, then you already use a partial fraction which turn out to be a logarithmic integral. Or you resolve partial fraction, then they turn out to be inverse functions. Then you end up with algebraic substitution to give you the final integral, how it appears, isn't it? So let us start with standard integrations. Standard integration. of course, in algebraic substitution. So the first one we'll see are the polynomial functions. How do we integrate the polynomial functions, isn't it? So remember we said a polynomial function or maybe a polynomial expression is just an algebraic expression with exponents, variables, and coefficients. So if you see any function in that case having coefficients, powers, and variables or exponents, so 2 is the coefficient, x is the variable, 3 is the exponent, isn't it? So anytime you see an algebraic function in that manner, then it is a polynomial function. So of course 2x cubed is an expression, but you see, so we say that is a function of x because it is in terms of a variable x, isn't it? So we say it is a polynomial function because it has coefficients, variables, and exponents, isn't it? So how do we integrate such cases? So if you have a polynomial function y to be a function of ax raised to power n, where a is a constant, where a and n are what? A and n are elements of R, meaning are real numbers. Real numbers. Are you seeing that? So where they are real numbers and n is different from -1. The reason being, when n is different from -1, this is what I imply. If someone gives you to integrate the x over x, this simply means you are integrating x raised to -1 dx, isn't it? So this means n is -1. You see? So such kind of integral is not obeying the polynomial. This kind of integral is a logarithmic integral. Are you seeing that? You get the of x, meaning n has to be different from -1. Are you seeing that? It is when it is a polynomial. Are you together? If it is -1, then it goes back to the Napierian logarithm, isn't it? Good. So, how do we integrate such a case? So to integrate this case, to integrate y, what do we have? If we have y, what is wrong with this pen? So we have y is, it has stayed for a long time without writing, ax raised to power n. So if you want to integrate this, what do? You integrate, what is the integral of y? If you introduce the integral then, what do you have? With respect to x, you get ax raised to power n plus 1 over n plus 1, then plus an arbitrary integral constant. Are we together? So what we are saying, anytime you are integrating a polynomial, you simply add 1 to the power and you divide with the resultant power after adding 1, isn't it? Yes. Are you seeing that? So an example of that case, if you have an example of such case, example 1, we've dealt with this before, we just doing a repetition, isn't it? Polynomial only. So you'll be told to integrate 3x cubed plus 2x with respect to x. So how do we integrate such a problem? So the first thing you have to identify, this is a polynomial function, isn't it? It is a polynomial function. We have the coefficient, variable, exponent. We have coefficient, variable, exponent. When the power is silent, it means it has a power of 1. So for you to integrate this, for you to integrate 3x cubed plus 2x raised to power 1 with respect to x, what do? You simply add 1 to the power. That is x raised to power 3. Then, what do? You add 1 to the power, then you divide by that resultant power. Isn't it?
Yes.
Then it is plus. Here we have 2x raised to power 1. For you to integrate that, you simply add 1 to that power, then you divide by that resultant power, which is 1 plus 1, isn't it? Then at the end of the integration, you add your arbitrary integration constant if you don't have the limits of integration, isn't it? You add your arbitrary integration constant. So the only thing you need to do now is to simplify, isn't it? So when you simplify, here you have 3 plus 1 is 4, isn't it? So you have 3 over 4, then x is raised to power 4, then plus 2, 1 plus 1 is 2, so 2 divided by 2 is 1, isn't it? Then plus x squared plus c, the arbitrary integration constant. So integrating any polynomial function, what you do, you simply add 1 to the power, isn't it? So we say n does not necessarily need to be a natural number. N just have to be different from -1, isn't it? It has to be different from -1. Meaning example 2, if somebody gives you a case like this, integrate.
Teacher, hapo kwa 3/4 alafu hapo hiyo tu imeenda wapi?
We have here 1 plus 1 is 2. So 2 cancels with 2, you remain with 1, isn't it? Good. So, example 2, if you have a case like this, if you are told to integrate dx over 3x cubed. Are you seeing such case? So, if you look at that, you see it is a polynomial, isn't it? Because it is, the power of x is different from 1. So this is the same as, it is the same as a third 1 over 3 x raised to -3 dx. So you can see, a third is the constant, x is the variable, -3 is the exponent, isn't it? But that -3 is different from -1, so it is a polynomial. Are we together? Or that, not that it is a polynomial, it is integrated using the polynomial way, in a polynomial way, isn't it? Are we together? Good. So here we have a third, then what do? We add 1 to the power, then we divide with the resultant power. Then at the end you add arbitrary integration constant. Whether you put it inside the bracket or outside the bracket doesn't matter. Because if you put it inside the bracket a third times c, you get a third c, that is another constant, another c, isn't it? So what do we have here? Simplify. 1, -3 plus 1 is -2. So a third divided by -2, you get -1 over, isn't it? Then x is raised to -2, then plus c. So negative means it is in the denominator, isn't it? So then it means you have -1 over 6x squared plus c. So any function which obeys the standard form of a polynomial can be integrated in a polynomial way. Are you seeing that? So the standard form of a polynomial is y is equals to ax raised to power n. So long as you see any function obeying this standard form of a polynomial, where n is different from -1, then you integrate it a polynomial way. Is that okay? Tuko pamoja?
Yes.
Good. Let's move to the second one. After polynomial functions, let's move to the next one. How do we integrate the exponential functions? So let us see how to deal with the exponential functions. How do we integrate exponential functions? Now, in exponential function is the simplest, just like the case in differentiation. Integrating an exponential function is very simple. So if you want to integrate the exponential function, like integrate exponential t dt, you are integrating exponential t with respect to t. If you integrate that, the answer is simply exponential t the way it is, plus the arbitrary integration constant if you don't have the limits of integration, isn't it? Are you seeing that? Meaning an exponential function, for you to integrate it, it remains the way it is. Is that okay? It remains the way it is. Now look at a scenario whereby from differentiation, if you have something like exponential 2x plus 1, if you want to differentiate this, the exponential function remains the way it is, then you differentiate the inner function, isn't it? So for you to differentiate this, the exponential function remains the way it is, that is outer function, then the inner function is 2x plus 1, isn't it? If you differentiate the inner function, you get 2. Differentiating 2x is 2, 1 is 0, isn't it? A constant, if you differentiate a constant is 0, isn't it? So if you differentiate this, if this is y, then this is y prime, isn't it? So 2 times this, you get 2 exponential 2x plus 1, isn't it? Meaning when you are differentiating an exponential function, you are multiplying the exponential function itself with the derivative of the inner function, isn't it? But now in integration, we want to see in integration what happens. Because integration, they will not give you the standard exponential function. What they will give you is to integrate a case like integrate exponential maybe 2x plus 1 dx. Now if you want to integrate this case, but we know that if you integrate exponential t, it just remains exponential t, isn't it? Now that is where the algebraic substitution comes in. Are you seeing that? That is where the algebraic substitution comes in. Meaning this inner function 2x plus 1, you let that 2x plus 1 to be t. So if 2x plus 1 is t, then what do we have? dx, you must get dt, isn't it? So how are we going to get dt? So we differentiate both sides with respect to x. If you differentiate both sides with respect to x, that is implicit differentiation. You introduce ddx on both sides of the equation, isn't it? So if you differentiate t, you get 1. Then you remain with dt over dx because you are differentiating t with respect to x. Say there. If you differentiate 2x, you get 2. Then you remain with dx over dx because we are differentiating an x variable with respect to x. So dx over dx is 1, silent, isn't it? If you differentiate a constant, you get 0. So from here, you make dx the subject of the formula because we want to do algebraic substitution, we want to substitute them, isn't it? So if you make dx the subject of the formula, 1 is just 1 to remain dt over dx, what do we do? So we find the reciprocal on both sides of the equation. So getting the reciprocal on both sides of the equation, we have dx over dt this side, that side we have 1 over. Then you simply take dt the other side, isn't it? So here we have dx is a half dt, meaning where there is 2x plus 1 you put t, where there is dx you put a half dt. So what do we end up with? We end up with exponential t, where there is dx, we have dt, a half dt, but a half can be factorized outside, isn't it? So you see we are now integrating exponential t dt, the standard form of an exponential integral, isn't it? So in that case, we have our half, which is a constant outside. If you integrate exponential t, you just get exponential t, then the end you have arbitrary integration constant if you don't have the limits, isn't it? And remember, if you are given the limits here to be 1 to 2, these are the limits of x, isn't it? Meaning you come and say, when x is 1, what is going to be t? Because you say the t is 2x plus 1. So when x is 1, what is going to be t? Where there is x, you put 1, t is going to be 3. Meaning now here you put 3, not 1, because this is now value of t. Are you seeing that? Then you go here again, when x is 2, what is going to be t? When x is 2, t is 5. Meaning here you now put 5, isn't it? Good. That is a case when you have the integration limits, isn't it? So from here, you now go back to the original. What you have the original, meaning where there is t, you put the value of t, isn't it? What was t? T was 2x plus 1. So here we have a half exponential 2x plus 1. Then you have arbitrary integration constant because we don't have limits, isn't it? So from there, what are you seeing? You see that for you to use algebraic substitution to integrate an exponential function, the derivative of an inner function must be a constant. Have you seen that? You don't need the whole of this process. All you need to know is that when you want to integrate exponential 2x plus 1 dx, you simply check the inner function. If I differentiate this 2x plus 1, do I get a constant? Are you seeing that? Meaning if you are getting a constant, then you can integrate it. Are you seeing the scenario? Yes. Are you together? So the derivative of the inner function of this exponential function is 2x plus 1. If you differentiate 2x plus 1, you get 2. So for you to integrate this exponential function, integrating an exponential function, it remains the way it is. It remains exponential 2x plus 1. Then you divide by the derivative of the inner function, which is the constant, which must be a constant in case of integration. Very different from differentiation. Have you seen that? Then plus the arbitrary integration constant. And that is what you have here. I have exponential 2x plus 1. Meaning that I have, you divided it by 2. You divide it to the derivative of the inner function in integration. The derivative of the inner function must be a constant. Meaning if somebody tells you to integrate exponential 2x squared plus 1 dx, you cannot integrate that like this in the form of a standard exponential function because the derivative of the inner function is not a constant. Have you seen that? Are we together? Yes. So if somebody will come later and give you very funny problems as we are going to see in ordinary differential equation. Let's say maybe you've ended up with maybe x exponential x squared, maybe plus 1, not just like that, yes, you want to integrate this. You cannot say, we are going to see a case of integration by parts later. This is a product of two functions. Anytime you see a product of two functions, you integrate by parts. Are we together? We'll see how integration by parts comes about. So x is a polynomial function, exponential x squared is an exponential function. So that is a product of two different functions. It's when you can use integration by parts. So it means anytime you see a question like this, sine t maybe equals 2t dt, or maybe sine t equals 3 dt, then you are told to integrate this. You cannot say this is integration by parts because it is a product of two functions. No, this is the same function. This is trigonometric, this is trigonometric. So it is one function, so there's nothing like a product of two functions. A product of two functions is two different functions where integration by parts comes about, isn't it? But this is also a product of two functions, but it is the same function. Both of them are trigonometric, so it is not integration by parts because you only have one function. Trigonometric, there is no any other function. Are you seeing? So the two functions must be different. Maybe one is polynomial and one is exponential. Maybe one is trigonometric and one is exponential. Maybe one is exponential and one is hyperbolic. One is hyperbolic, one is in trigonometric. The two functions we're looking for the product must be different. Are you seeing that? So what do you do in this case? You go to factor formulas and product identities in trigonometry, isn't it?
Yes.
Because this is very simple. Sin t equals t. If you have that is even a sine double angle formula. Sin 2t. Sin 2t is sine 2 sin t equals t. So you divide both sides by 2. Meaning when you have sin t equals t, you put a half sin 2t. So there you have a half constant outside, then you put sin 2t inside. You've reduced it to one thing. Are you seeing that? Uko pamoja?
Yes.
Good. This guy is always with us. So that is how we deal with cases of exponential functions. The derivative of the inner function must be a constant. So what I was trying to explain, I don't know whether I've explained it. If you have x exponential x squared dx, you cannot say this is integration by parts because it is a product of two functions. Are you seeing? Because of course it is a product of two different functions. This is polynomial, this is exponential. See, you use integration by parts, but you cannot use it. Why? Because the derivative of the inner function of an exponential function is not a constant. Are you seeing? It's not a constant. So it is not integration by parts. Now it's algebraic substitution. How does algebraic substitution? You go back to differentiation. You ask yourself, if you have maybe y to be equivalent to sine exponential x squared, if you take exponential x squared itself. So if you differentiate this with respect to x, meaning implicit differentiation, you introduce ddx on both sides of the equation, isn't it? If you do implicit differentiation here, for instance, introduce ddx on both sides of the equation. So this side, if you differentiate y, you get 1. Which derivative do you remain with? dy over? Because we are differentiating a y variable with respect to x, isn't it? Is equal to, if you differentiate an exponential function, it remains the way it is. So it means here you remain with the exponential 2x, then you differentiate the inner function, isn't it? In differentiation, it doesn't matter what is in the inner function, isn't it? So if you differentiate x squared, you get 2x. So you multiply the outer function with the inner function like that, isn't it? So we now have dy over dx is this. Are you seeing? So you now take the x's on their side, you do separation of variables. Y is to remain on their own, x to be on their own, isn't it? So separation of variables, you take dx the other side, isn't it? So here we have dy is equals to 2x exponential x dx. But what do we have here? X exponential x dx, meaning these two can be factorized outside. Or can be removed, so you can divide both sides by 2, so that you have a half dy is equals to x exponential x squared dx. So what does that mean? If you introduce the integral on both sides of the equation, algebraic substitution, meaning instead of this integral, it is just a half dy. So a half dy is the same as a half, then you are integrating dy. What are you integrating here? You are integrating a polynomial, isn't it? You are integrating a polynomial because there is no y, meaning it is y raised to power 0. Anything raised to power 0 is 1, isn't it? So if you integrate this, what do you have? You have a half. What do? You simply add 1 to the power and you divide by the sum power. Then arbitrary integration constant if you don't have the limits, isn't it? Are we together? Now from there, what do you see? So if you integrate this, you have a half y over 1, meaning I have y plus c. What is y? Algebraic substitution, we go back. What was your y? Remember you said your y was exponential x squared from here, isn't it? So where there is y, you put the value of y. So you over half exponential x squared plus c. So you see you've integrated that. This is the answer. And you will not use integration by part. Algebraic substitution. Have you seen how it is coming about? So you must identify the facts. The fact is that if you have a product with the two functions, does it obey a case of a standard exponential function? Because you know a case of a standard exponential function, the derivative of inner function must be a constant, isn't it? So if you see that inner function is not a constant, automatically you go back to algebraic substitution. Are we together? Good. So that is how to deal with the exponential functions. So if you see such cases of exponential functions, let's see maybe example number 2. Example number 2. Just slowly, we are just digesting it bit by bit. By the time we reach partial fractions, then we will now start the business, isn't it?
Yes.
Yes. It will now be more simple and more direct. So integrate exponential 3x plus 4 dx. So if you integrate that, what do you get? You simply check. The derivative of the inner function must be a constant, isn't it?
Yes.
So what is the inner function there? 3x plus. Then when you are integrating an exponential function remains the way it is. It remains exponential 3x plus 4, isn't it? Then you divide by the derivative of the inner function, which must be a constant. Are you seeing that? So the derivative of the inner function, if you differentiate 3x plus 4, you get 3, isn't it?
Yes.
Then at the end, you have arbitrary integration constant. If you like, you can write that meter is the term exponential 3x plus 4 plus c, isn't it? Are you together? So before you integrate an exponential function, you must check the derivative of the inner function must be a constant, isn't it? Good. Let's move to the next one. That is number. This was number 2. This was number 2. We are now going to number 3. Logarithmic function, isn't it? So we see when we were dealing with the hyperbolic functions, complex numbers, all the functions we've dealt with in the past, they are dealing with the Nappierian logarithm, isn't it? The natural logarithm, because it is the natural logarithm which can be expressed in form of an exponential function, isn't it? It is the base to base e, meaning if you have exponential x to be equals to 3, x is the index, exponential function is the base, isn't it? So the index is the logarithm of the corresponding number to a given base, meaning x is the logarithm of 3 to base e. So anytime you have base e, that is the Nappierian logarithm, isn't it? So log to base e is the same as ln, the natural log, Nappierian logarithm. So x is ln of 3 instead of log to base e. Is that okay? So when we are integrating logarithms, we are basically dealing with the natural logarithm, any logarithm to base e, the ln logarithms, isn't it? So how do we do such cases? It is the simplest of all. It is the simplest of all the things you will be integrating, and it is the most common. Logarithmic functions. So logarithmic functions, if you are told to integrate dt over t, the answer is simply ln of t plus c, and you are done. The arbitrary integration constant, meaning if you integrate dt over t, the answer is ln of t. I'm just adding c because I don't have the limits of integration, isn't it? Yes. Are you together? So somebody will come and give you this. So now see where I was adding standard integration with algebraic substitution. Somebody will come and give you this. So the first thing when you want to deal with the logarithmic integration, the first thing you need to check is what? Is the algebraic substitution. When it is working, then it is in many cases it will turn out to be logarithmic differentiation, integration. Are you seeing that? So when you are given example 1, example number 1, if you are told to integrate dx over x plus 3. Are you seeing such a case? Integrate dx over x plus 3. How do we integrate dx over x plus 3. This is very simple. What you need to check, first of all, what you need to check when a function is turning out to be logarithmic, it is always like this. The function in the numerator is always a degree less than the one in the denominator. We said the degree of a polynomial, like this case, is the highest power, isn't it? So you said the degree of a polynomial is the highest power. Meaning if you are given a case like a polynomial x raised to the power 5 plus x raised to the power 4 maybe plus x plus 3x plus 2. So we say this is a polynomial of the fifth degree. The degree of this polynomial is 5. You check the highest exponent, isn't it? The highest power. Are you seeing that? So the degree of this polynomial is 5, isn't it? So if somebody gives you x squared minus 2, the degree of this polynomial is 2, because 2 is the highest exponent of power. Are you seeing that? So you see in the numerator, denominator here, the highest power of x is 1, meaning the degree of the polynomial in the numerator is, in the numerator, the degree, highest degree is 0, because in the numerator here we have x raised to the power 0. That is why it is silent, because anything raised to the power 0 is 1, isn't it? Are you seeing that? So the degree in the numerator must be 1 degree less than that in the denominator. It's when in most cases it will turn out to be logarithmic. Are you seeing that? Are we together? So if you see that the degree of a polynomial in the numerator is less than the degree of the polynomial in the numerator by only 1 degree, then you test algebraic substitution. Are you seeing that? And if the algebraic substitution is not working out, then you'll see go back to the cases of partial fractions, so that when you resolve it, part of it will remain logarithmic because logarithmic obeyed the order previously, isn't it? And part of it will turn out to be maybe an inverse function. A case I'm talking about is a case like this. Before I solve this, I still need to explain this. If you have, maybe you are given maybe 2x, maybe 2x plus 1 over, maybe 2x plus 1 over x squared plus 3x maybe plus 1. Then you are going to integrate this with this factor. So you can see the degree of the polynomial in the numerator is 1, isn't it? The degree of the polynomial in the numerator is 2, meaning the one in the numerator is less than the one in the numerator by 1, isn't it? But if you check that, you will end up seeing that when you do algebraic substitution, it will not come out to be the standard form of a function which will turn out to be logarithmic. Are you seeing that? So what you do is that you will separate, you find if you try to resolve it, by factorizing this. You know you can factorize this to come out with the 2 polynomials, isn't it? So that when you factorize it, part of it will go to maybe the inverse function and part of it will go to remain the logarithmic. Because when part of it goes and you find maybe, let's say, if you have something like maybe 1 over x squared plus 1, you find that kind of derivative is tan inverse of x plus c. But you can see the degree numerator just is not 1 degree less. It cannot be that. But this one will come out maybe from it if you resolve the partial fraction. Are we together? So let us now see how to deal with this kind of problem. The kind of problem like this, if you see the kind of problem like this, automatic, the answer is automatic. ln of x plus 3 plus c. How does that come about? This comes about like this. You use algebraic substitutions. Once you see it is obeying the case of a degree in the numerator less than the one numerator by 1, isn't it? So what do you say? What is in the numerator? The x plus 3. It is supposed to be what? It is supposed to be t. So you say let t to be x plus 3. So once you let t to be x plus 3, meaning you must eliminate the x, isn't it? So you must get rid of the x. How do you get rid of the x? Meaning you differentiate this. You have t is equals to x plus 3. So for you to get the x and the t, meaning you differentiate with respect to x or t, does not matter because implicit differentiation, you can introduce ddt on both sides of the equation, you can introduce dx on both sides of the equation, then later you rearrange to make any of them the subject of the problem. You end up with the same thing, isn't it? Yes. Are you seeing that? So if we want to integrate, differentiate this, t is equals to x plus 3. If I introduce ddx on both sides of the equation, implicit differentiation. So differentiating t with respect to x, if you differentiate t, you get 1, isn't it? Then you remain with which derivative? dt over dx. Then can you differentiate this? If you differentiate x with respect to x, you get 1, you remain with dx over dx, isn't it? Dx over dx is 1, silence, If you differentiate a constant, you get 0. So it means we have dt over x equals to 1. But what do we want? We want dt, meaning we make dt the subject of the formula, isn't it? So we take dx the other side, see there? So if you take dx the other side, we have dt is equals to dx. Then you automatically go back to algebraic substitution. So your problem is dx over x plus 3 is equals to where there is dt, you put the value of dt. Dt is the same as? No, where there is dx, I mean. Dx is the same as? dt. So where there is dx, we put our dt over x plus 3. X plus 3 is the same as? T. So at the end, you have dt over t, which is the same as ln of t, if you integrate, isn't it? But in that, we don't have limits of integration, we have plus c. So if here was limits of x, meaning you have to look for limits of t. You cannot use limits for x for limits of t. See there? Because t is x plus 3. Meaning if here you have 0, 1, where there is x, if you put 0, meaning for t you are going to have 3. See there? Are we together? Tuko pamoja? Good. So, how have you seen that? You've not reached the final answer. The final answer must be x, isn't it? So it means anywhere you see t, you put the value of t. The value of t is x plus 3. So it means in the head, I have ln of x plus 3 then plus c. Are we together there? Good. So that is how to deal with the logarithmic problems, the logarithmic integrals. Example number 2 maybe. We are still digesting them. We've not started doing them. We are still digesting them. We have to digest each and every function before we go to now when the functions are combined, isn't it? Example number 2, we told to integrate 2x plus 3 dx over x squared over x squared plus 3x minus 7. You want to integrate this problem. Now what have I said? I've said the first thing you check, these are polynomials. The polynomials in many cases will turn out to be logarithmic in nature if you integrate. Are you seeing that? Are we together? So you test if algebraic substitution is working. That is the first step. If algebraic substitution is not working, is when you resolve into partial fractions. Don't rush into resolving a problem into partial fractions before you test algebraic substitution. And remember, partial fraction you also resolve if the degree of the polynomial in the numerator is greater than or equals to the one in the denominator, isn't it? Are you seeing that? Are you getting the concept? That is when you resolve. But when the degree is less than, you cannot resolve into partial fraction. You can only separate, isn't it? Separate is like this. This is what I mean with separate. Separate means you have, instead of 2x plus 3, meaning whatever is in the denominator is a common denominator, isn't it? Whatever is in the denominator is a common denominator. So this is like saying it is 2x over x squared plus 3x minus 7, then plus 3 over x squared plus 3x minus 7. Then the whole of that is what you are integrating with respect to x, because what is the denominator is the common denominator. You cannot resolve into partial fraction if this one is less. Can you remember? You can only resolve into partial fraction if the degree of the polynomial in the denominator is equals to or greater than the one in the denominator. Are you seeing that? If it is equals to or greater than, you have to resolve into partial fraction. This is what I mean. When somebody gives you x squared plus 2 over maybe 3x squared minus 4x plus 3 to integrate with respect to x. You see, the degree of the polynomial in the denominator is 2. The degree of the polynomial in the denominator is 2. Meaning they are equal, isn't it? You cannot integrate that. You have to resolve into partial fractions. Are you getting the point? Is that okay? Oh, somebody gives you x cubed plus 2x squared minus 7 over 3x squared minus 2. You can see the degree of the polynomial in the numerator is greater than the degree of the polynomial in the numerator. So you have to resolve. You are getting the concept?
Yeah.
And for you to, when it is greater than, before you resolve, what do you do? What do you do before you resolve? You do polynomial division. Because polynomial division will get rid of the highest power, isn't it? You do polynomial division. You remember these things I'm just passing through them because you did them in algebra, isn't it? These are things you did in algebra, so I'm just talking about them. Before you resolve that, you have to do polynomial division to reduce this power, isn't it? Polynomial division is like saying if you have 27 over 3, 27 over 3, you have to reduce this 27 fast before you check, isn't it? 27, maybe 27 over 4. 27, 4 goes in 27, how many times? 6 times. Then you remain with 1, 6 plus 1 over 4. So you cannot resolve it. You cannot reduce that power by polynomial division. But these are you seeing that? Are we together?
Yeah.
Good. We are going to see all those cases later. So, what I was saying, before you separate, you have to check if the algebraic substitution is turning out to be a logarithmic function. Are you seeing that? You check before you separate. You know this one you cannot do polynomial division because it is already less, isn't it? So can you check? Check the one in the numerator. We are checking, that's the first step. Okay? Check. What is in the denominator is what you substitute, because in the denominator is where we have t. Are you see? Denominator is where we have t. So it means t is equals to x squared plus, isn't it? So if you introduce dx on both sides of that equation, what do you get? dt. If you differentiate both sides with respect to x, here we have dt over. If you differentiate x squared, 2x dx over dx is 1, isn't it? Plus
3.
Serious. Then you make dt the subject of the formula, meaning you take dx the other side, isn't it? So when you're taking dx the other side, the whole of this must be one thing, isn't it? So what do we get here? You multiply both sides by dt, you get by dx, you get dt is 2x plus 3 dx. Good. So are you seeing? Meaning where there is 2x plus 3 dx, you put what? dt. And where there is x squared plus 3x minus 7 is the same as
T.
Meaning algebraic substitution is working. So you don't separate, you don't do anything. You go direct to algebraic substitution. Have you seen the scenario? Are we together? So it means this problem is the same as 2x plus 3 dx. The whole of this you've seen, it is dt. You put 20t over x squared plus 3x minus 7, the whole of that you substitute to dt. So you have dt over t. What is dt over t? We found it is ln of t plus c, isn't it? Then you substitute the value of t to get back your integral. Meaning where there is t, you put the value of t. What was the value of t? What is t? T is the same as the whole of this, isn't it?
Yes.
Meaning where you have t, you put the whole value of t, which is x squared plus 3x minus 7. So we have ln of x squared plus 3x minus 7, then arbitrary integration constant at the end of integration. Are you seeing? So it means anytime you are doing integration, you don't, whether you are given the limits, don't deal with the limits. You only introduce the limit after you've arrived at the final answer. Are you seeing that? You only introduce the limits after you've arrived at the final answer, because the final answer here will do what? Will not change the limit. Because if this limit was from 0 to 1, for instance, meaning the moment you change it to t, you put limits of t. Serious? Are you seeing? So instead of putting the limits of t, you just do the indefinite integral, the one without limit. You do the indefinite integral until you get the final answer. After getting the final problem to be like this, is when you go back to the equation. So if the equation was like in this case, if the equation was like integrate from 0 to 1, 2x plus 3 dx over x squared plus 3x minus 7. So you've seen, you've integrated indefinite integral without limits, isn't it? And without limits, what have you found to be the answer? You found the answer to be ln of x squared plus 3x minus 7. So once you do this, you don't add c. What you simply do, you now put the limits 0 to 1. Then you come here and you put the limits 0 to 1 instead of arbitrary integration constant, because you are given a definite integral. Have you seen the scenario? Yeah. Meaning you only reintroduce the limit later after you found the answer for the indefinite case. Is that okay? Good. Let us move to the next one. After logarithmic function, what do we have there in line? Trigonometric functions. Now where you have, when you want to deal with the trigonometric functions, here is now where we have the task. You have to recall those trigonometric identities the way you used to sing them. You start elementary identities. How are the elementary identities? How are the symmetric identities? How are the Pythagorean identities? How are the compound angles, the cosine difference angle formulas, the cosine sum angle formula, the sine, tan, cosec, secant, sine and sum and difference angle formulas, the double angles, are you seeing? The half angles, the factor formulas and the product identities. All of them are coming back here. And they're very simple. Are you seeing that? So, that is number 4. So number 4, trigonometric functions. How do we integrate a trigonometric function? Very simple. Now here is usually tested, you are always very happy about it, isn't it? Now, the first thing you need to recall is this. I want to use the differentiation procedure to spell out how this thing is simple. If you want to integrate a trigonometric function, you only need to do 2 only, nothing else. You only need to know how to differentiate either a sine or a cosine, isn't it? Because if you have a sine is the reciprocal of cosecant. Meaning, when you have cosecant, you put it in terms of sine, isn't it? When you have tan is sine over cos, isn't it? When you have sec is 1 over cos, isn't it? Are you seeing? So it means for you to do integration of trigonometric function, you only need to know how to integrate a cosine function and how to integrate a sine function. That is all you need to know, isn't it? Are we together? You don't need to know how to integrate those other ones. Those other ones are going to come out by themselves. Is that okay? So let us see. If you have, for instance, let me use the concept of differentiation for you to spell it out clearly. If you have y to be equals to sine t, differentiate y. If you differentiate y, you get dy with respect to t. If you differentiate y with respect to t, you have dy over t is equals to? If you differentiate sine, what were you getting? Cos, isn't it? So if you differentiate this, you get dy over dt is cos t. So what do? You do separation of variables, meaning variables t to be on their own, variables of y to be on their own, isn't it? So it means this dt goes on the other side of the equation, isn't it? So what do we have here? We have dy is equals to cos t dt. But what do we want? We want y. For us to get y, we introduce the integral on both sides of the equation. We introduce the integral, isn't it? So if you integrate y dy, what do you get? You get y. Why are you getting y? Because remember, integral of dy is the integral of y raised to 0. That is why here is 1. Because y raised to 0, anything raised to 0 is 1, isn't it? So you simply add 1 to the power and divide by the standard power, isn't it? Meaning integrating dy, you simply remain with y. Because it is y raised to 0 dy. That is why it's silent here. Is that okay? Good. So it means on this side we remain with y to be equals to integral of cos t dt. Have you seen the scenario? Then now substitute. What is y? Where there is y, put the value of y. Y is equals to what? Sin t. Meaning where there is y, put y. Y is sin t. So we have sin t is integral of cos t dt. What does that imply? What it implies is that when you are integrating cos t dt, the answer is sin t. Then you now add y between integration constant. So you can see it is the opposite. When you are differentiating cos, you are getting negative sign. Are you seeing? But now when you are integrating cos, the sign changes. You get positive sign. Have you seen the scenario? The sign changes. Check the other case. The other case, if you have y to be equals to cos t. Can you differentiate with respect to t? Differentiate y with respect to t? So this is the first case. The first case we've seen, if you integrate a cosine function, you get positive sign. Isn't it? Are we together?
Yes.
So if y is equals to cos t, this is second case. What do we have here? Differentiate y with respect to t. You get dy over dt to be equals to, if you differentiate cos t, what do you get? Negative sin t. Remember, I'm not differentiating the inner function because the inner function, if you differentiate, is 1. That's why I'm not talking about it, isn't it? Because if you differentiate t, which is the inner function, you get 1. So it is negative sin t times 1, which is just the way it is, isn't it? Are we together there?